All right. Today I want to finish up the most of this lecture about reviewing for the test tomorrow. We stopped on quotient, the reaction quotient yesterday. We talked about Q. There are three ways or three things that you do whenever the reason you're going to use Q. Remember, Q is used when you're not when. Good. When you're not at equilibrium. Okay. We left off by saying, what do you do when you solve for Q? One. Okay. You solve for Q. What was number two? Good. Compare to K. Very good. And the last one was determine the shift. Okay. So that's the major purpose of using Q. Now, when you find the value of Q, it's how you compare it. Now, they list it in the wrong way. I like listing it in alphabetical. So when K, again, is greater than Q, we know we shift which way? To the right. Again, you cheating using the points. And when K is less than Q, we know we shift to the left. So again, that's basic rundown using Q versus K again. So today what I want to do is we're going to skip on the back page, we're going to skip 13.6a. This is the steps for solving using Rice tables. I'm going to come up with something more encumbersome, if you will. It's going to cover all the ways and the more proper steps and using my words and a little bit easier than this. So what I want you to do is skip down to 13.7 and let's go to Le Chatelier. So Le Chatelier is basically getting you to learn how to recover an equilibrium situation. So when you get unbalanced, you want to get back to balanced. So there's several ways we can affect concentration. Number one, what is the only thing that will ever change the value of K? Temperature. That's it. If we're dealing with any of these things, you'll never change the value of K. Reason why is because when you shift and you make more products, what happens to your reactants? When you shift and make more products, what happens to your reactants? They decrease. So what does that do to the actual numerical number of K? It balances it back out. So that's why the value of K will never, ever, ever change unless you change the temperature. So we're going to look at what happens when you just figure out how to shift K. So if a change is imposed, the position of the equilibrium will shift to. Major thing is to reduce that change. Remember, we always want to get back into equilibrium. So if we add something, how do we shift? Good. We shift away from an addition. If something is removed, how do we shift? Towards. Very good. So those are the two easy ones. Okay? But now I want to focus on something real quick. And let's use this equation because we always come back to it. Okay? Excuse me, this is a 3 and this is a 2. Now, please pay attention to this because your multiple choice tomorrow is there's a lot of Le Chatelier questions. So you need to know how to answer Le Chatelier. If I add some N2, my first question is, what way are we shifting? Towards the what? Good. Towards the products. We're going to shift right. Now, this is where it gets a little bit tricky and you have to think through this because they're going to ask you about individual species within the reaction. So, Jordan, what happens to the actual number when you add nitrogen? What happens to its concentration value? Increase or decrease? If you add, yeah, it's going to increase. What happens to this, Braden, if we're shifting right, making more of it? What does its number do? It increases. Well, Riley, here's the major part. When we go away from it, what does this value do? It decreases. So here's the question. They're going to ask you what happens to this individual species. Or the question could be, we're going this way, so which one of these decreases? Or we're going this way, which one of these increases? So be very mindful of exactly what they're asking for and what happens to each species. On the reverse, what if I tell you that I remove some N2? What way are we going to shift now? We're going to shift left. So what happens to the concentration of this thing? You're pulling it out. Exactly. So it decreases. So, but when it's going to recover it. So, but before it decreases. What about this one? What's going to happen to it? It's going to increase, and what happens to this one? Decrease. So you have to look exactly what happens to their. So if I take some out, it has to go down. Okay. So that's exactly what we want to look at.
Are they going to say like? Are they going to tell us like one of the if we have two more than one?
Yes, they'll tell you which one.
They'll tell us which one is.
Exactly. So going back into this. So we've covered the effects of change in concentration. Now let's talk about a change in pressure. Now this is a whole lot of stuff. Okay? We know it in a much, much, much simpler way. If you increase the volume, what happens to your pressure? The pressure decreases. Make sure you understand that. If you decrease your volume, what happens to your pressure? Your pressure increases. Now, how do we shift? If we increase our pressure, what do we shift? Okay. How do you shift? To the fewest moles of the gas. To fewest moles of gas. So, looking at this particular equation, what if I tell you, now, you know, all these are gases. What if I tell you that I decrease your volume? If I decrease your volume, what's happening to your pressure? You're increasing the pressure. Well, what then happens? How do you shift if you increase the pressure? You shift which way? To the fewest moles. Well, how many moles of gas are on the left-hand side? 4. How many's on the right? 2. So what way are we going to shift? We're going to shift towards the products. Very good. That is for increasing the pressure, or the same thing is reducing the volume. Now let's do the opposite. What is the opposite if you decrease the pressure? How are you going to do it? So let's go back to this. And if we decrease our pressure, how are we going to shift? It's my computer. To the highest moles of gas. Okay, exactly. So that's exactly how we're going to shift. So it's just the opposite. So if you decrease the pressure, you go to the highest moles. Guys, you are going to see these exact type of problems. So be aware of them. So remember, there's two things you can do. You can change the concentration. Will the value of K change? No. But the shift will occur. If you change your pressures, the value of K will still stay the same, but you will be able to change and shift. Now the final and the last part. This is the one that is the most important. This value will change K. And the most important thing is it is going to depend on the thermicity. You have to know exo or endo. Now, first of all, what will tell you, hey, here's the temperature, what you're looking for. You have to either look for this. You have for a delta H value, or it says something about heat energy. Okay, that's what you're looking for. You have to look for something that says delta H or heat energy. Elliot, what is the sign of an exothermic reaction? Negative. So if delta H is negative, it's what? It's exo, right? Hannah, what is the sign of an endothermic? Positive. So if it says positive, then you know it's an endothermic. Here's the biggest part that people get the misconception of. You've got to then determine what side is it on. This is the most important part. For an exothermic reaction, what side is your heat on? It's on the product side. That is extremely, extremely important, because when you're solving this, you've got to determine, well, where do I add my heat at? Which side is it going to go on? Well, how do we know that exothermic is a product of heat? Because it's being released. It's given off. Exactly. Well, what about endothermic? What are you doing with heat in endothermic? You're putting it in, so that means it must be a reactant. It's always that way. If it's exothermic, it's a product. If it's endothermic, Troy, it's a what? Reactant. Okay? So make sure you stay on with that track. But once you have determined what side the heat is on, it goes back to the same rule. You shift what from an addition? Away, and you shift to a removal. Shift towards a removal. All right. So let's look at this reaction one more time. And again, and the reason we use this one is because it's just an easy one to talk about, and we need to know what it is anyways. Okay. So let's say for the time being, some crazy reason, they tell me delta H is 1896 kilojoules. What's the sign of delta H? Positive. So what side is your heat going to go on? Reactant. How do you know? Perfect, because it's under. So I know my heat is going to go right here. So what if then they say we raise the temperature? What is that saying you're doing? You're adding. You're increasing delta H. So you are adding heat in. Do we agree? Same rules apply. You shift how from an addition? Away, so you're going to shift this way, correct? This is where you have to think. You have to say, okay, I know that K is going to change. Why is K going to change? Because temperature. Now, let's talk about exactly why K changes. What is, you heat them up, you speed them up. Does that change the rate? What is the basic definition of equilibrium? Rate of the forward equals the rate of the reverse. Well, if you change your rate, then the rates must change. Therefore, the K will change. Now, we are making more products. So here's the kicker. This is the most important part. K, we know, is equal to products over reactants. So Patrick, which number is going to increase in this set? On top. So if the on top number increases, then what does K do? K also increases. So if you ever make more product, what does K do? Increase only when the temperature changes. When the temperature changes, if you make more product, K increases. Well, let's do the opposite of that. What if I say, okay, I'm going to put it in an ice bath? What do you think an ice bath would do? Cool it down. Will that decrease your temperature? Yeah, we're going to remove some temperature. How are we going to shift? We're going to towards the left. In this case, what are we making more of? More reactants. So what's going to happen to K? K will decrease when you make more reactants. Again, the reason why this bottom number will increase, giving you a smaller value. Does that make sense? Okay, Bez, you with me? Jordan, you with me? Okay. Again, that's the exact reason all of this is going on. Any questions? So going back to this, let me make sure, just so you can have this in your examples and you have this written down. For this one right here, when it clears, this is for an increase in temperature. Okay, letters A and B. This is for an increase in temp. Okay, number 2 is talking about a decreased temperature. So make sure you get that. And it just refers back to 1A and B. Now, let's look at some examples of problems that were actual AP chemistry questions. That's not what I want. This is what I want. Okay. You guys should have this worksheet, right? My first objective for you, write the K expression. If you can't write K, you can't do anything. If you can't write K, you cannot do anything. So your K expression should look like this. Now, let me ask you this. Can you do KC or KP in this case? Yes. Why can you do KP? They are all what? Gases. If there's ever an aqueous, can you do KP? No. Why not? Pressures are only caused by gases. So you can do the KP. I'm going to write both of them for you. So the KC is using brackets. It's SO3 raised to the second power, SO2 raised to the second power using brackets, and then finally we have O2 in brackets. Now, KP is going to use what? Parentheses. Now, it's not only parentheses, but it's that P as well. Because remember, it's partial pressures, parentheses and the P. Partial pressures, the two P's. So it's the P of SO2 squared and the P of O2. So either one of these would work. On the where? It's SO3 on top, SO2 on the bottom. Okay. They will specify on the exam which one they want. They'll either say, give me KP, give me KC. Normally it will be KC, but again, they could say KP. How they normally do this is they'll say, give me KC, convert it to KP. Do we have that equation? Yeah, we do. We're going to actually work on this. So let's actually work the Le Chatelier principles they're asking you to do. Now, briefly account for your prediction. So I'm going to write a bunch of stuff in and explain, because they're not just going to want to know how do you shift right or left. No, multiple choice, yes, but for your response, justify, explain, predict, use words. Now I'm going to kind of do a shorthand. You need to do this longhand version. So first of all, they're decreasing the volume. Let me think. Decreasing volume does what to my pressure? All right, that increases my pressure. Well, in that case, if I increase pressure, I shift to the what? Good, the fewest moles. Now, what I need to do is I need to look for the fewest moles of a gas. Are all of my reagents? Now, what are reagents? They're both, either one. Are any of them non-gases? No. So how many moles of a gas do I have on the left? 3. How many do I have on the right? 2. So what way am I going to shift? I'm going to shift right, because there are the fewest moles of a gas on the product side. So what am I going to make more of? More products, and here's the kicker question. Think before you speak. Think before you speak. Does K go up, go down, or remain the same? Troy, what does it do? Why does it remain the same? Temperature is the only thing that affects K. Did they mention anything about changing the temperature? No. So K, and again, I'm just going to write constant. You can write remain the same. You can write doesn't change. Whatever you want to write. I'm just going to write constant. Yes, ma'am.
So like whenever it's a free response, what can we write?
I would say that you're going to shift right towards the products because there are fewer moles of a gas on the product side. That's how I would explain it. Okay, something of those. That's a good question. How would you explain this on free response? I'm going to shift to the right because there are fewer moles of a gas produced on the product side, and that is the rule. Okay, looking at B. What's wrong? All right, it's going to take a little bit to get there. Now let's look at B. You are adding. Now, when I think adding, I think what? I'm going to think away. So you are adding oxygen. So Claire, if I'm going to add something there, what way am I going to shift? Very good. Shift to the right towards the products. Now, again, you shift away from an addition. Last question. Here's the kicker. K go up, go down, remain the same. Remains the same. So K is constant. And again, why is K constant? Yeah, because the temperature is not affected at all. Now, last question, and this is very important. Look at the phrasing of the equation up top. It gives you the equation, and then they give you something very interesting. They say delta H is negative. Now let's look at letter C. Raising, soon as you see temperature, what should be going off in your head? What's going to change? K will change, so we got to figure out how it's going to change. What are you looking for when they say something about temperature? You're looking for delta H. You're looking for the sign of delta H. What do they tell you the sign of delta H is, Avery? Avery, what's the sign of delta H? Okay, it's negative. Now, so Avery, since it's negative, what does that tell me about its thermicity? It's exothermic. Now, okay, it is on the product side. Very good. So since I know that, I can add heat to the side. So Elliot, since I'm raising the temperature, am I adding heat or lowering heat? Or removing heat? If I raise the temperature, am I going to add something to this or remove something? You're adding heat. So if you're putting it in, Jordan, what way am I going to go? It's the same rules apply. You add, you go away. So what way am I going to go? Go left towards the reactants. Exactly right. Okay? That's the same rule applies. Yes, ma'am. Alexis. Yeah, when it's exo, you're going to add it to the products because exo means to give off. Therefore, it is a product. Okay? So you're going to shift to the left. So again, raising temperature, I know that I'm going, that the reaction was exothermic because delta H was negative. Therefore, heat is a product. Okay, so I shifted away from the addition. So I'm going to shift towards the reactant side. So it's a reactant shift. Now, here's the biggest thing. What are you making more of? More reactants. So here's the biggest question. How is K affected? K decreases, exactly. Why does K decrease?
Because the products are going down and the reactants are going down. The reactants are up.
You're making more reactants, and K is equal to products over reactants. Well, this bottom value is getting larger. Okay? The bottom value is getting larger, so K must come down. So if they ask you how is K affected, K will decrease. Okay? So again, if you've noticed, the only thing that changes K is temperature. You have to understand that. Okay? You have to understand that. Let's look at the second part. My first thing I want you to do, write the K expression. Write the K focused. All right, so here's the major deal, and I guarantee you, because some of you weren't paying attention when you did this, you messed this up. And here's why. What is this little letter telling me right here? It's a solid. There are three things that never go in a K expression. What are those three things? Solids, pure liquids, and then liquid water. Now again, we say liquid water because it's many forms. But here's the deal. There's water, but it's a gas, so it goes in. So when you wrote this, the K expression should have been CO to H2 all over H2O. That should have been the K expression. Yes, sir. I don't know. Aqueous. Okay. So really, the only things that go in a K expression are gases and aqueous solutions. Now, they tell you this, and I'm going to go ahead and jump on this because I know I'm probably going to have to use it. Delta H is positive. So what is that telling me? It's endo, and since it's endo, what side is it going to go on? It's going to go on the reactant side. Okay, so again, we're already establishing that. Let's go ahead and add the heat factor to this. The heat factor, okay? All right, so here we go. An additional H2 is added to the equilibrium. Now, here's the deal. At a constant volume. So is your pressure going to change? No, so there's no shifting because of that. So we are adding. So what do we do from an addition? We shift away. Shift away. So we're adding. Now, which side are we adding to? Products or reactant side? We're adding to the products. So since we're adding to the products, how are we going to shift? So we're going to have a reactant shift to the left. Okay? So that's why, because we are adding to the product side. How is K affected? K is constant. B. Temperature. Temperature. You got a question? Okay. So as soon as we see temperature, something should be going off in our mind. We're going to have to figure out how K has changed. So what it says is the temperature of the equilibrium mixture is increased. Since it's increased, I know that I'm going to have to go away because it is added. Now, here's the deal. Delta H is positive. Therefore, it is endo. So since it's endo and I'm increasing, means I'm adding here. So what way am I going to shift? Right or left? Right towards the product. So I have a product side shift. So what's being made more of? You have more products. So here's the final important question. How is K affected? How do you know it's increased? Has nothing to do with that. Because it shifts towards the products. So when you shift towards the products and because of a temperature increase, K will increase because of that. Now, what I want you to do is I want you to do the final two. Do C and do D by yourself. So this time, we're going to take the volume and we're going to decrease it. Well, if you decrease the volume, Bezel, what happens to my pressure? If you decrease the volume, the pressure. If I take you and stick you in my office, what's going to happen? Okay, first of all, the volume gets smaller, so what happens to the pressure? The pressure increases. So since the pressure increases, how are you going to shift? Elliot, how are you going to shift if the pressure increases? Figure it out. If the pressure increases, how are you going to shift and why? Or why are you going to shift that way? Elliot, I'm asking you a question.
They're distracting me now. I'm like, if you increase the pressure,
Come on, Elliot.
you just right.
Thank you. Claire, is that what you're going to say?
Yes, but you weren't calling me.
To the fewest moles. Now, here's the deal. We've got to figure out the fewest moles. If you look at it as it stands, if you include the solid, they're even, right? Well, here's the deal. Solids cannot produce pressure, so you have to get rid of it. So how many moles do you have on the left? 1. How many do you have on the right? 2. So what way are we going to shift? We're going to shift to the left. So we're going to have a reactant shift. So we're going to shift to the left based on that fact. Now, what happens to K? K is constant. Why is K constant? Very good. It does not have to do with temperature. Now, the last part, it says graphite pellets are pulverized. First of all, what is pulverized? Beat, crushed, smashed into small pieces. But here's the deal. Graphite is made up of what? Solid carbon. So does it matter if you mash this stuff up or leave it as pellets? Is it ever going to affect the equilibrium? So no shift. Exactly. Very good. So if it gives you something about a liquid, if you're adding a liquid, if you're adding a solid, there's no shift. Here's 2 more I want you to write down. What if I tell you I add argon, the noble gas? Why is it no shift? Very good. Inert gases do not affect equilibrium. So if you add a noble gas or an inert gas, it does not affect equilibrium. And the last one, what if I add a catalyst? No shift, because all it does is speed it up. Now, could that potentially affect K? Yes, it could potentially affect K. Why? It's lowering the activation energy. It's altering a different pathway. Therefore, the rate should increase because the time should decrease. So it can affect K, but again, if they're never going to ask you if you add a catalyst, what happens to K? There's no shift, but K could potentially be affected. All right, any questions, sir? No, because it won't. That's one of those weird kind of questions I'm not quite sure how to answer. I see what you're saying. You're putting in a gas. You have more things bouncing. I see what you're saying, but I think because it won't react, it will not cause the reaction to happen any faster or slower because it will not make this gas break apart into that. Does that kind of make sense? I know what you're saying. If you add in a gas, shouldn't the pressure increase? No, I mean it's because it's an expandable thing. But if there was a reaction going on, it would not affect the reaction itself. So an inert gas, I'm not quite sure. I think it would affect the pressure, but it would not affect the reaction. Okay? All right. Last little thing. Let's see. I think that was it on that. I actually want to look at a free response question. Again, like I said, I'm going to film some rice table problems later, but there are a few things on this that I actually want you to work through and let's go through just because it's good to see. So this is 1995 free response question. I sent you this in Google Drive. You have all of the free response questions. We're only going to work A through C, so I didn't want to give you the whole thing and get the max out for no reason. But the first thing that I want you to notice is letter A. What is the mole fraction of CO2? What symbol represents mole fraction? Chi. Mole fraction is represented by chi. So now, what does mole fraction mean? It's the mole of what? A over what? Total moles. Over total moles. Now, here's the deal. What are they asking you for? They're asking you for the mole fraction of CO. Here's one part. What do you notice about these units right here? What are those types of units? Molarities. So these are molarities. Well, here's the good part about mole fractions. You can use molarities in mole fractions. So you can use a molarity in chi. What is the molarity of CO? Good. So it's 0.55. What is the total amount of moles? This is where you have to be careful. What do you notice about this right here? There's two of them. So do you have to account for both? Yes, that's where some people mess up, is they'll just put all of these once, but you have to notice there are two things in this particular column. So it's 0.5 plus, which is accounting for those two things, and then 1.1. So what does that equal? 0.55 divided by 1.6. Yeah, this is 5. In the end, to two significant figures, it will come out to be 0.34. Okay, so that will be the mole fraction of CO. Now, part B, using the equilibrium concentrations, calculate Kc. This is what I want you to do. I want you to write the K expression and plug these values in to your K expression. I know you don't have a calculator, but if you have one, you could give me the answer. So write the K expression, and then plug the values in where they should appropriately be. So go ahead and do that. All right, so we need to be able to write the K expression and then plug these values in. The K expression should be very, very simple for you, because what do you notice about all of the types of states of matter? They're all gases, so will all of them go in? Yes. So Kc, now, could you possibly do Kp? Yes, but what do they ask you for specifically? They ask you for Kc. So this is going to look like this. Now, first of all, guys, simply writing this will earn you 1 point. So if they ever ask you for a K value, please, please, please write the K expression. If you don't, you could possibly lose a point. Make sure you write this and fill it in. It's the longer step, but if you do it, your life will be so much easier, I promise. So both of the ones on top are 0.55. Now, would it be appropriate to do that?
Yeah.
Why? Because both of them are on top are the exact same value. And 0.20, and I got these on the bottoms backwards, but you can, it's the exact same thing. Did anybody plug this in by chance to get an answer? Okay, I have the answer. It is the answer is to two significant figures. That right there. Okay. Now, final part, I want to run through C. Determine Kp from that value. How do you go from Kp or Kc to Kp? The politically correct equation, which is what? Kp equals Kc RT to what? Delta N. What is delta N? The change in moles of what? Of gases. This is the most important part. Please get this right here, what I'm fixing to do. Change in moles of gases. How many moles of gas are on the left? 2. How many moles of gas are on the right? 2. What is delta N? 0. If you look on your test objectives, I said this. When you raise anything to the 0 power, what does it turn into? That is what the answer is. So when delta N is 0, Kc equals Kp. So this is your answer. So Kp is 5.0. Yes, ma'am, Alexis.
Okay, so you just have to do that and then.
Yeah, you would actually show the equation, you plug everything in, and then solve it. Okay? Yeah, stuff like this, yes. Okay. Now, today, if you have time to come back this afternoon, that's fine. I'm going to work through a few rice tables. I'm going to finish out the notes of when to use a rice table, how to use a rice table. I'm going to send you that video. Make sure you watch it tonight. Guys, be here by 7:10 in the morning. You are going